Hi, I'm Gabriel Baravdic from Linköping University. Today, I will present our paper, GPU-accelerated SL0 for multidimensional signals for ICPP PDADS. This work was done by me, Gabriel, Jonas Unner, and Ehsan Mianchi. In the field of compressed sensing, we seek a sparse representation S for measurements P. We have that S is sparse under a dictionary D and sampled by a matrix phi. We aim to reconstruct S by minimizing the L0 norm, that is, the number of non-zero elements in S. This, together with the condition that the error is bound by a user-defined parameter, epsilon. For this case, the smoothed L0 algorithm, SL0, solves this problem for 1 dimensions. However, this algorithm can be computational heavy to compute on the CPU, depending on the signal length and the structure of the signal. Our approach is to extend this to the multidimensional signals, or tensors, where each dictionary is small. Here, each A is an equivalence sensing matrix, where A equals phi times B. We aim to find a sparse tensor S for a set of A's with given measurements P that is also a tensor. We also aim to speed up the computation of the algorithm on the GPU, where the signals or tensors are large. We do this by using a Cholesky factorization for computing the pseudo-inverse of A. To further speed up the algorithm, we parallelize all operations and compute the input signals batch-wise. This is the algorithm. Here, you first compute the pseudo-inverse of A by a batch-wise parallel Cholesky factorization. This will act as an initial solution. For the rest part, we compute the batch-wise multidimensional computation of the GPU, where we perform the iterative routine and compute all arithmetic operations in parallel. We analyze the arithmetic intensity and conclude this expression. We break down the algorithm and compute the lower bound, where this fraction is larger than 1. In this expression, SNP represents the number of elements in the tensors SNP previously shown. M is the number of rows in A, and K is the number of columns. Finally, N is the number of dimensions of a tensor. As a result, we have that the algorithm is arithmetic bound for S greater than or equal to 8, as well as for P. This holds for tensors with at least 3 dimensions or higher. We evaluate the algorithm on light field datasets. The 2, A and B to the left, are light fields with 8 by 8 views, meaning that we process 64 images from different angles. The input signal of these datasets are tensors with 5 dimensions. We also evaluate for C and D, which are light field videos. We use 4 frames from these videos. These datasets have 6 dimensions. For all of these datasets, A, B, and C, and D, we split them into smaller tensor patches and sample the patches for reconstruction. We will now look at 3 tables that show timing results for the algorithm between a GPU and a multi-threaded CPU implementation. Our first evaluation shows timing results for light fields. Here, each data point has 5 dimensions. We vary the sample ratio for the measurement tensor P for reconstruction. You see that the magnitude of the speed up for the GPU compared to the multi-threaded CPU is large and maintained through different sampling settings. Finally, we are able to run this with up to 100,000 data points in parallel. In our second evaluation, we test the algorithm for light field videos with the tensors of size 6 or 6 dimensions. Here, we vary 2 settings, the spatial size for the data points and the total signal length. We increase the spatial size and fix the sampling ratio for reconstruction. We see that the speed up increases compared to the multi-threaded CPU for large tensors, and we are able to achieve up to 27 times faster speed up. At the third and final evaluation, we test the algorithm for light field videos with different sampling ratios. We increase the sampling ratio over 4 frames for reconstruction. The speed up is an order of magnitude larger for the GPU implementation over all sampling ratios. As a conclusion for this paper, we have done a convergence analysis of the multidimensional SL0 algorithm. This is to guarantee that we achieve a sparse solution under certain conditions. We also present an implementation of the multidimensional SL0 algorithm on the GPU, which computes the algorithm in a parallel batch-wise fashion. Our evaluations show that large datasets, such as light fields as tensors, can be reconstructed in practical time. Additionally, the algorithm can be used for other types of data. Finally, we have that the algorithm is arithmetic bound for tensors with at least 8 elements. Thank you for your attention.